Hello, welcome everyone to the first lecture of Safety Critical Controls of Robots. Uh, in this lecture, we'll see the motivation behind safety critical controls, meaning of safety, ways to achieve safety, and the topics that we'll cover in this course, the last. So, before we start, due to the low retention rate of long lectures, I'll try to keep the lectures as short as possible. And if not possible, I'll try to divide each lecture into the sub lectures of 20 to 25 minutes each. A little bit about me. I am a PhD scholar at Stochastic Robotics Lab in Indian Institute of Science, Bangalore. I am currently working on safe robot learning and control, especially using control barrier functions. So, let's start with the motivation. So, right now, autonomous systems have quite an exciting prospect in the future and in the present as well. So if you see, there are a lot of research that is going on in autonomous systems, especially self-driving cars. Companies like Tesla or even conventional companies like Volkswagen, Mercedes are trying to develop self-driving cars. So, but while we work on autonomous systems, we require a minimum level of guaranteed safety that we require from these autonomous systems. So, what we expect is the performance of autonomous systems should be higher than that of human beings, even in the case of maintaining safety, right? So, for an example, if we want to trust a self-driving car, we should expect it to outperform human beings in terms of detecting the obstacles and also avoiding them faster and more efficiently, right? So, um how do we achieve what is the meaning of safety? Let's first see that. It depends on the application actually. So, for example, if we are seeing self-driving cars, safety might mean that you maintain a safe distance and you also drive within the speed limits, right? In case of self-driving cars or robots like drones, unicycle, legged robots, etc., safety might mean that you don't collide with the obstacles, other vehicles or other robots, right? While you operate in your while you try to achieve something else, right? Uh, in case of legged robots, foot placements are very crucial and very critical. So in cases like you want to step on, like you want to step on stones, right? Or you want to step on stairs, foot placements are really very important. So safety in this case means you place the foot in a very accurate way and at a very accurate angle so that you land perfectly and you don't slip like this child is slipping in this case, right? So in the case of artificial pancreas, it might mean that the pancreas do not release lot of insulin or too less insulin, and that too they release at a safe rate so that it does not turn out to be life threatening for the patient. Okay, so intuitively it means that safety means that nothing bad happens in general, right? So how do we achieve safety? So to ensure safety, we might there's a way to involve a human in the loop, or say a safety pilot. So which means there will be a human being who will maintain safety and make sure that the robots or the systems don't go out of the safety region. But a major drawback in this case is that the system is not scalable and it depends on the capabilities and the attention of the human being, right? Another way is to create backup controllers or backups, a list of them actually, and you have to make sure that you take care of all the unsafe cases in the list, and that is why it is not very scalable. Next way is to guarantee safety using formal guarantees, right? So basically this way includes modeling the system, and then giving some mathematical guarantees, and calculating the controller, so that you're able to formally guarantee the safety of the system. And this is what we'll talk majorly about in this course, right? As you'll see. um, so methods to achieve safety with formal guarantees. So what do we really expect from a ideal safety controller? So basically we might so we need a controller that minimally deviates from the reference. For example, if I am moving at a particular set trajectory, and there's an obstacle in my way, I don't want to change my path altogether. I just want to minimally evade it and then recover my original path back after I avoid the obstacle, right? So that is why uh, we need some minimal deviation from the reference. Next is we want the controller to be very computationally efficient, which the reason why we need this is because we need real time safety, right? And because basically if I want to if I'm moving in a cluttered environment where there's a lot of obstacles, or I'm working in some other environment, if I if I if my controller, the way to calculate the control input is not very computationally efficient, I'll hit the unsafe region first, and then my controller will give me a safe control input. So I do not want to be very computationally heavy. If possible, we want to reduce as much computational uh, load as possible, and make it more efficient. And obviously at last we want some formal guarantees, so some mathematical guarantees if we can give. This will make my safety controller, this is what I expect from my ideal safety controller. So one way is to one way to achieve safety is to use non-linear model predictive control. We can also use artificial potential fields, and we can use control barrier functions. We'll see all these concepts in this course, right? And so basically in this course we'll cover topics starting from some prerequisites on constraint optimization, basics of linear control theory, non-linear control theory, and optimal controls. If you are well versed with these topics, you can actually skip these topics and directly come to the topics that you feel that you want to learn from this course, right? Then we'll start with the nonlinear MPC and ways to achieve safety, artificial potential field, edge reachability, Hamilton Jacobian reachability. Then we'll construct the concept of control barrier functions, very similar to how control Lyapunov functions are constructed. So we'll touch upon the topics of control Lyapunov functions, and then go to control barrier functions. Then we'll see what special kind of CBFs are present, like exponential CBFs or higher order CBFs. And at last, we will cover some recent research topics in control barrier functions like collision cone CBFs or neural CBFs. So that's all for this course. Thank you very much for seeing this lecture, and I hope that you continue watching the future lectures. Okay, thank you.